So let's keep talking about the chemical equilibrium in this second model of chapter 15. By the end of this model, you will be able to predict the direction of a reagent given the equilibrium constant and the concentration of reactants and products. Also, you will be able to calculate the equilibrium concentrations given the equilibrium constant and all but one equilibrium concentration. Also, you will calculate the equilibrium concentrations given the equilibrium constant and the starting concentrations. And by the end of this model, you will use the Le Chatelier principle to predict how changing the concentration, the volume, or the temperature of a system at equilibrium affects the equilibrium position. So, is there some way to determine if the reaction has reached equilibrium? And if not in equilibrium, which way does the reaction goes to reach equilibrium? So we have uh, another quotient that is called the reaction quotient, that is Q. So when we calculate Q, Q will let us know if we are in equilibrium or not. Q looks like the equilibrium constant K, but the values used to calculate it are the current condition, not necessarily those for equilibrium. To calculate Q, one substitutes the initial concentration of reactants and products into the equilibrium expression, and once you have Q, you compare that value of Q with the equilibrium constant. So, which are the possible values of Q that we can find? First, nature always wants the Q to be equal to K, because if we determine that Q value that is equal to K, that means that we are in equilibrium. So if Q is lower or smaller than K, nature will make the reaction proceed to the products because we want to increase the value of Q. And we know that Q and K there have the same expression, products over reactants. So if we want to increase the Q value, we need to increase also the product. So that's why when we have a Q lower than K, the reaction will proceed to more to the products. If Q is equal to K, that means that we are in equilibrium. And if Q is larger than K, that the reaction will make proceed to the reactants. Okay, so because the Q is larger, we want to decrease that value of Q. So the way that we can do that is by increasing the reactants, the concentration of the reactants. That will make the Q lower until it's smaller until it's reached the uh, equilibrium constant value. So how can we calculate the equilibrium concentrations? If you know the equilibrium constant, you can find equilibrium concentration from initial concentrations and changes based on stoichiometry. You will set up a table similar to the ones used to find the equilibrium concentration in the previous model, but the change in concentration rho will simply be a factor of x based on the stoichiometry. So we're going to use again the rice example, that the rice type table example that we used before. For this reaction, the reaction of nitrogen gas plus oxygen gas producing 2 moles of nitrate oxide. So the initial concentration, this one is going to be in partial pressures. Okay, so the initial pressure of nitrogen will be 0.79 atmosphere. The initial pressure of oxygen will be 0.21 atmosphere, and the initial pressure of NO will be 0. So the expression of this of the equilibrium constant for pressure will be the partial pressure of NO time elevated to power of 2 divided by the pressure of nitrogen and the pressure of oxygen. This will be equal to 1.0 times 10 powers minus 5. That's basically the constant equilibrium constant for this expression. So that means that we can create what are the partial pressure of reactants and products when the system achieves the equilibrium. So we can create the table that we used before. The reaction is here on the top. Initial change equilibrium. We have at the initial point 0.79 atmosphere for nitrogen, 0.21 for oxygen, and no pressure for NO. So the second part is basically the change. we don't know what is the change. When we don't know a specific value, most of the time we use a variable. So in this case, we're going to use the x as the variable because we don't know what is the change. Okay, but we know that for the reactance, it's going to be minus x because you're consuming that pressure, okay, for nitrogen and oxygen, and because you're producing NO, the change will gonna be 2x, and it's gonna be 2 because you have 2 moles here in the products in the original reaction, okay, so that's why you use the 2x, and nitrogen as well as oxygen, they have just a coefficient of 1, so that's why it's minus x both because both of them are reactants, and plus here to NO because the NO is a product. So that means that at equilibrium, we will have basically when we add initial plus the change will be 0.79 minus x, 0.29 minus x, this will be 0.21 minus x in equilibrium, and 0 plus 2x will be 2x. So these are the values, okay, or the representation of the pressure for each of them at equilibrium. But we don't have a specific value yet. But we know that the expression of the equilibrium constant is the following. So it's going to be the partial pressure of nitric oxide divided by the pressure of nitrogen and oxygen. And we can look for the values in the table. It will be 2x squared divided by 0.79 minus x times 0.21 minus x. We can solve the top part of this fraction. It will be 4x squared. Okay, so now we can look, because we know the value of the equilibrium constant, we can calculate this pressure of all of the reactants and product at equilibrium. So to do that, we're going to assume that this x is really, really small. The x on the denominator is really, really small. So we're going to eliminate it in this expression, okay, to simplify a little bit that math and avoid to use the quadratic expression, because if not, we need to use the quadratic expression. So let's use first this assumption that this x is really, really small. It's not going to affect that much these two values. So if this is close to 0, this is close to 0, the bottom part will be simplified like this. And now we can maybe look for the value of x knowing the equilibrium constant as we know before at the beginning of this problem. So let's solve this equation. We have this value, so let's multiply the bottom part. 0.79 times 0.21 is equal to 0.17. Then let's move the 0.17 to the right side by multiplying both sides by 0.17, and we're going to have this expression for x2 equal to 0.17 times 1 multiplied by the 10 powers minus 5. Now we can solve the right side of this equation. So for x squared, it will be equal to 1.7 times 10 power of minus 6. Let's divide by 4 in both sides so we can leave the x alone in the left side. So now if we divide by 4, the x squared will be equal to 4.14 times 10 power of minus 7. And now we can look for the square root of x squared, and the x will be equal to 6.44 times 10 power of minus 4. So this is the value of x that we obtained by assuming that the value of x was really, really small in the last slide, okay? So now we need to determine if that value of x is really, really small. How can we do that? We need to check if the change is less than 5% of the maximum amount, okay, of the initial part. So for N2, the change is 6.44 times T10 powers minus 4 divided by 0.79. This is the initial pressure that we have for nitrogen, multiplied by 100, and this will be equal to 0.08. This is smaller than a 5%. For oxygen, basically we have the same thing, okay? So, but in this case, we'll divide by 0.21 because 0.21 was the initial pressure for oxygen. We'll multiply by 100 and we have a total of 0.31%. So because both of them are lower than 5, it was correct to do that assumption, okay? So now we need to look for the concentration at equilibrium. As we know, at equilibrium, it will be for the pressure for nitrogen 0.79 minus x, the x value that we determined before. And this is basically the same pressure, okay, for nitrogen. For oxygen, we have the same thing. This the expression of of the pressure of in equilibrium for oxygen. We substitute the x, and we're gonna have also basically the same value, because remember that this was really small, so that's why we could make the assumption that x was really small. But for nitrogen now, the pressure at equilibrium will be 2x, so it'll be 2 times 6.44 times 10 power of minus 3 minus 4, and the pressure at equilibrium for nitric oxide will be 1.28 times 10 of power of minus 3 atmosphere. So those are the partial pressure at equilibrium for this chemical reaction. So let's do another example now using concentration instead of partial pressures, okay? So 1.0 liter flask is filled with 1.0 mole of hydrogen gas and 2.0 mole of iodide gas at 448 degrees. Given a Kc of 50.5 at 448 Celsius degrees, what are the equilibrium concentration of hydrogen, iodide, and hydrogen iodide? Hydrogen iodine and hydrogen iodide. So here we have the equilibrium reaction, and our table. We basically substitute all the value. The initial concentration is 1 molar and 2 molar for hydrogen and iodine, and for hydrogen iodide is 0. The change is going to be minus x because here we have one coefficient here. And for hydrogen iodide is going to be plus 2x. These two are reactants, so that's why we have a minus, sign of minus before the x. And this one is a product because we are increasing that, we are creating more products, so that's why it is a plus 2x. And here at equilibrium, it will be 1 minus x, the concentration of hydrogen, 2 minus x, the concentration of iodine, and 2x, the concentration of hydrogen iodide. So let's set up the equilibrium constant expression, filling in the equilibrium concentration from the table. So this is the expression of the equilibrium constant. So by looking at the table, we have the expression, the concentration of Hi at equilibrium is 2x, so it'll be 2x squared. And the concentration at equilibrium for hydrogen is 1 minus x, and for iodine is 2 minus x. And also we have the value of Kc, that is 50.5. So let's try to simplify this math first by assuming that these values of x are close to 0, okay? And by that, determine this value of x and see if that will work. So let's go to do that. Here, we just eliminate the x at the denominator, okay? And now 1 times 2 is going to be 2. And here, from here, we can divide 4 divided by 2. So 4 divided by 2 is equal to 2. So that's why the equilibrium constant will be equal to 2x squared. That is equal to 50.5. Now we can divide on both sides by 2. So we can have the x squared alone. And then to this value of 25.3, we can do the square root, and that will be the x, 5.02. Now, but if you remember how we determined, we need to see if that change, okay, for the reaction is going to be less than 5% of the initial concentration. The change for both is minus x, okay, so it will be 5.02. But 5.02 divided by 1 and 5.02 divided by 2 is going to be way more higher than 100%, okay? So that means that we can assume that this x is smaller, that really small, so we can cancel that x. So we need to work with the quadratic expression. And to show you this example, let's see the following video. So here we have the expression to determine the value of x. So let's solve the top part of the fraction. Parenthesis 2x, parenthesis power of 2. This will be equal to 4x squared.
Now the bottom part, we need to multiply 1 times 2 and 1 times minus x. So this will be equal to 1 times 2 will be equal to 2, and 1 times minus x, it will be equal to minus x. Now we need to multiply this minus x to 2 and then minus x to minus x. So we're going to have there 2 times minus x, this will be minus 2x, and minus x to minus x will be plus x squared. All of this will be equal to 50.5. Okay, so let's solve the bottom part. It will be equal to 4x2 divided, and let's rearrange. Let's put here the first x squared minus x plus minus 2x. This will be equal to minus 3x plus 2. This will be equal to 50.5, the value of the equilibrium constant. Now let's multiply on both sides by x squared minus 3x plus 2. This will be multiplied by x squared minus 3x plus 2. And now we can cancel this denominator, so we're going to have something like this. This will be 4x2 equals to 50.5 times x squared. This will be equal to 50.5 x squared. Then we multiply 50.5 times minus 3x. This will be equal to minus 151.5 x, and 50.5 times 2. This will be equal to plus 101. Then we're gonna take this value and put it with all this equation and leave this equal to 0. So this will be equal to 50.5 x squared minus 4x squared minus 151.5x plus 101. Okay, so now this will be equal to 46.5 x squared minus 151.5x plus 101. So let's move this a little bit up. And now we have here the values for our quadratic equation. Remember that our quadratic equation is going to be equal to x is going to be equal to minus b minus b plus minus the root square of b squared minus 4ac, and we divide this by 2a. So that means that this is our a, this is the value of b, and this is the value of c. So we substitute those values in that equation, and that means that x is going to be equal to minus, in this case, minus 151.5 plus minus the root square of b squared. This will be minus 151.5 squared minus 4 times a, that will be 46.5. We're going to run a little bit out of space here. Let me put here like a, this is not part of this. Cool. 46.5, sorry about that. And then we'll multiply this by c, that is 101. So the root square goes all the way down to here. And we divide this by 2a. So 2 times 46.5. So this will be equal, x will be equal, minus the minus will be 151.5 plus minus the root square of 151.5 square. This will be 22,952. And this is minus, so here we have um, 4 times 46.5 times 101. This will be equal to 18,786 divided by 93. Now, this x will be equal, let's see if I have more spade downs here, perfecto. So this will be equal to 151.5 plus minus the root square of 4,166, and this divided by 93. So now let's do the two possibilities to solve this equation. Let's go through here for the plus and here the minus. So that means that um, actually let me rewrite this. Before that, let us solve the top part. So all that. So this will be equal to 151. X will be equal to 151.5 plus minus 64.54, and when we divide this by 93. Now let's do the two possibilities, one by adding and the other one by subtraction. So if we add 151.5 plus 64.54, this will be equal to 216.04 divided by 93, and this will be equal to 2.32, and this will be 1x. The other x, you can find it by subtracting the top 151 to the two values, 151.5 minus 64.54. This will be equal to 86.96 divided by 93, and this x will be equal to 0.935. And here we have the two possible values for x. One will be 2.32, the other one will be 0.935. So now we need to use this x and use check with the equation to determine the x value that we showed before in the slide before. So we'll go to that point now.
So since x must be subtracted from 1 and 3.3, maybe the number is not exactly this one because some of significant figures, but it's close to 2.3, the ones that we determined in the video. This makes no physical sense because we must um, it's going to be we're going to subtract that from 1, so it results in a negative concentration. So the value instead of 2.32 is going to be 0.935. So for the hydrogen in equilibrium, 1 minus 0.935 is going to be 0.065. This is the concentration of hydrogen at equilibrium. For iodine, it was 2 minus x, so it's going to be 2 minus 0.935 is going to be 1.065, the concentration at equilibrium. And for hydrogen iodide, it was 2x, so it's going to be 2 times 0.935, so the concentration is 1.87 at equilibrium. So these are the three concentrations of the reactants and the products. So let's change up subjects and talk about the Le Chatelier principle. Um, the Le Chatelier established the following concept. If a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of that disturbance. One of those disturbances could be the change in the concentration of the reactants or the product. If the system is in equilibrium, adding a reaction component will result in some of it being used up. Okay, so for example, here we have the reaction of nitrogen plus hydrogen producing ammonium. If we add to this equilibrium more hydrogen, if we increase the concentration of hydrogen, we're going to have a higher concentration here of hydrogen. This will shift the equilibrium to the right because we need to decrease the concentration. Okay, so the only way to decrease the concentration of hydrogen is shifting the equilibrium to the right. So because of that, we're going to have an increase of ammonium. Okay, and that is what we can see here. Here, this is an equilibrium, but when we add the hydrogen, it suddenly starts to rise the partial pressure of ammonium because we are producing more of ammonium due to the excess that we add to the reactant. Also, because nitrogen also is a part of that reaction and we are shifting to the right, that means that we're consuming nitrogen. So here we have the pressure at equilibrium, and suddenly when we add hydrogen, the concentration of nitrogen decrease because we shift this value to the right. Okay, so we can shift this to the right by increasing this concentration. And what happened? What do you think if this is in equilibrium and we increase the ammonium, the NH3? What is going to happen? Because we're increasing this side, we need to decrease the concentration. So it's the only way is going to the left. So if we increase the concentration of NH3, the shift will be to the left. If we increase the concentration of the reactant, the shift will be to the right. But also we can remove reaction components, and this will really result in some of it being produced. So if we remove hydrogen, that means that this concentration will decrease. To reach equilibrium, we need to produce more hydrogen. So if we remove this, the shift will be to the left. As well as if we remove nitrogen, the concentration of nitrogen will decrease and we will shift the equilibrium to the left, so we can produce more nitrogen because we're decreasing that concentration. Now, if we decrease the concentration of NH3 of the products, then this will go down. So we need to produce more of ammonium. So we will shift, or the shift will be shift, the equilibrium will be shift to the right. Okay, in that way. So that's basically the effect if we change the reaction, the reactants or the products at equilibrium. Also, we can see an effect if we can change the volume or the pressure, specifically if we have gases in equilibrium. When gases are involved in an equilibrium, a change in pressure or volume will affect the equilibrium. We have, for example, this reaction, 2A producing 1B. Both of them are gases, okay? So here we have 2 moles of A in the reactants and 1 mole of B in the product. So if we change, we have this initial volume, but if we increase this volume, that means that we'll decrease, okay, the pressure. This will favor the side of the equation with more moles. So that means that if we increase this volume, we're going to favor the shift to the left because we're going to have more moles there. So that means that at increasing that volume and decreasing the pressure, we're going to favor the side that has the higher number of moles. And if we decrease this volume, okay, if we decrease this volume, that will increase the pressure, then we will shift the equilibrium to the right or to the side that we have less number of moles. So that's why we have a lot of the B here, because by decreasing the volume, it will increase the pressure and we will shift to the side that has lower number of moles. So this is basically the effect that or how will affect the pressures and the volume to a reaction that is in equilibrium. The third one is change in temperature. So it's important to see if the reaction is an exothermic or endothermic. An endothermic reaction is the reaction that absorbs heat. The exothermic reaction is a reaction that releases heat. So if we absorb heat, that means that the heat must be in the reactants. Okay, so when it's an endothermic reaction, you will have the heat in the reactant. If it's an exothermic, that means that you release energy, so you have energy, heat in the products. So when endothermic, heat acts like a reactant. Adding heat drives the reaction toward products. We're going to see that in a few minutes. And the exothermic, heat acts like a product. So if we add heat, this drives a reaction toward the reactants. Okay. So let's see an example here. We have this complex of cobalt that is hexahydrate, and it will react with 4 moles of chlorine. This will produce this other complex of cobalt with chlorine plus 6 moles of water. Now, this complex has a pale pink color, and this complex has a deep blue color. Okay. Now, this reaction is an endothermic reaction, okay, because delta H is larger than 0. So that means that the heat must be in the reactants, okay? So at equilibrium, we had heat in the reactants, this pale pink complex and this one in blue complex. So what will happen if we remove, um, let's go here back. What will happen if we, for example, add heat? If we add heat, that means that we need to consume that heat. So this will go to the right. And the color that we will have is a blue, deep blue color in the solution. If we remove heat, if we cool somehow, if we cool this equilibrium, then we need to produce more heat to reach again the equilibrium. So we must shift this equilibrium to the left and we will have a pale pink solution. So here, this purple one is at equilibrium. If we add heat, we will must shift this to the right so we have a deep blue color in the solution, and that's what happened here. When we add heat, is a deep blue color, and if we remove heat, we cool down the solution, then we must the equilibrium must shift to the left so we can increase the production of heat, and we will have a pale pink color. So when we cool the solution, it will turn the solution to a pink color. So in an exothermic equilibrium, taking again the sample of the Haber process for producing ammonium from the elements, this process is an exothermic one. So you will think that if it's an exothermic, the heat is in the products. One would think that cooling down the reactant would result in more products, because if we cool the system, that means that we have the heat at the product, so we will shift that to the right side. But we have a situation, and is that the activation energy for this reaction is really high. So that means that even though we decrease that temperature, it's not gonna be efficient, okay? Because the activation energy for this reaction is really high. So if we have a higher activation energy, what we can use to decrease that activation energy? A catalyst. So this is the one instance where a system in equilibrium can be affected by a catalyst. So the only way that a catalyst will affect an equilibrium is if this reaction has a higher activation energy. So the catalyst increases the rate of both the forward and the reverse reaction, and the equilibrium is achieved faster, but the equilibrium composition remains unaltered. The activation energy is lowered, allowing equilibrium to be established at lower temperatures. So that here we have the profile, the reaction pathway versus energy. Here we in black we have the uncatalyzed reaction, and the green one is the catalyzed reaction. So we can see here that that catalyst reduced the activation energy for this reaction. And here in the rate, we can see here this is time versus the formation of the product. The rate for the green one, that is the one that with the catalyzed, proceed more rapidly, is faster than the one without the catalyst. So with this, we finish our module number 15 of chemical equilibrium.